Okay, welcome. We have some clarifications on clustering which we did, and we will continue with clustering algorithm. We have learned something on classifying, and classification basically of data which is labeled. Okay. You do what is called supervised learning or supervised techniques. When you have unlabeled data, we do unsupervised, which is also called clustering. So, basically you have data, you have labeled and unlabeled. There are also other cases which are partial labeling, we will not look at that. So, this we saw a problem where we had some data distribution like this, and this was the classifier. Of course, in higher dimension the classifiers can be like this, and even other what one calls the decision boundary. So, this is class 1, this is class 2 separation. But today most data is unlabeled. Classifying unlabeled data is termed clustering. So, how do we go about? For this it will be useful to know what typically classifiers perform. Okay. So, how it is done? You have data, you split the data into 3 portions. It is called training set, testing set and validation set. So, typically you have data, you break it %x%, y%, z%. So, x plus y plus z is 1, which is your 100% data. You use x% data for training the classifier. Why I am mentioning this is, when we get into clustering we have serious problem training the classifier. This is test data used for testing trained classifier. You have validation data which will validate trained and tested classifiers. Of course, sometimes this is shuffled. So, you have a new x1, new y1, new z1 out of this, and this shuffling is called m-fold crossover. Typically you shuffle this 3 or 4 times and train, test and validate. When you train, test and validate on the same data set, it is called close validation. What is important is particularly practical application. this validation needs to be done by a third party external data set. This kind of validation makes it universally acceptable. Such luxuries may not be there when we go for clustering. So, we also see some interesting performance, which is also performance of classifiers. Typically, the following is what one can see. Suppose you have features, that is number of features, percentage error, which is a measure of the performance of classifier. Typically, as the number of features increase, the performance improves and then starts getting worse, which means there is some place where you have optimal number of features to be used for classification. This is for a fixed data set, fixed data size. Then other issues involved of classifiers is training time. This is number of features. As the training time increases, the error drops. This is for training data. But the same thing on test data starts looking like this. This is the point where you must stop training. So, what works well on training data need not work well on testing data. This is the portion where, corresponding to things like this, here overfitting happens, here excess training. Similarly, for validation it is even more interesting, where validation data can look like this performance. So, this is the time where you stop. So, performance on training data is not a good indication. Testing data is better, meaning performance as seen from testing data, eventually what is accepted will be validated. So, do not train too much. Next, do not use too many features. This is like overfitting. Of course, do not use less also, underfitting. Then use optimal number of features. Okay. Then this cycle of train, test, validate. This is what tells what is a good classifier. Classifier for the problem and the data. data for this. Of course, you have different many types of classifiers. You could use simple linear, Bayes method, other statistical distribution based, so many things are there. So, what we have given indication is how these issues of classifier look like. We will now move on to unlabeled data which is related to clustering. Clustering you resort to clustering when you have unlabeled data. For example, you have data like this. Typical clustering answers would look like this: one cluster, second cluster, third cluster, fourth cluster, or maybe this is separate. Okay. Now, the same thing can be done in a different way. Here you perhaps have one cluster like this, second cluster here, third cluster. You can have one more solution. Which is one cluster here, second cluster here. So, how many clusters make a good solution? Suppose you have n data points, two extreme answers are one cluster, all the data point, the other is n cluster, n point cluster, that is n 1 point clusters. So, both answers are definitely wrong, it lies in between. So, just like good classifiers, how do we find good clusters for data? For this we use something interesting, we use a metric. Metric means distance, more generally a measure. Okay. We also need an objective way of doing this. First thing, we have some help that clustering is both a natural process meaning we attempt to find natural clusters in data. We use two parameters. One is internal meaning within cluster, within a cluster, and another external, that is. So, this is quite intuitive. Internal, that is within a cluster, distance between data points should be small. Externally, distances should be large. Which basically means the following. Suppose we were to find a cluster of data, one cluster and say another cluster. We want the distance between them, meaning the distance between the centroids of these two, this distance to be large, and distance between the points here to be small. This must be as small as possible, this must be. So, basically it is quite intuitive when you collect people together and they form groups, you will see that this is a very natural phenomena. You see it in wildlife, in nature, like that is the reason the birds of the same feather flock together kind of terminology is being used many times. Okay. So, how do we go about doing this? We also use what is called a measure of similarity. So, you call similarity measure as S xi comma xj, two data points, it could be vector, it could be matrices, whatever, must be large if xi and xj are similar. We can also use a dissimilarity measure, call it D, between two data points xi comma xj is small if xi comma xj are similar. Similarity of two vector data points can be easily seen by the cosine rule, right. How similar they are is how well they are correlated and if angle and all that. Okay. So, this is really what is used, and typically for an algorithm which has so many data points to be clustered, it runs as follows: randomly select some centroids, and select all the points within a radius epsilon I or epsilon j from that. Okay. And if there is one more point, this will merge, and such that the distance between centroid Ci and Cj is very large. So, this is the most common simple clustering algorithm. So, given data, simply select randomly k centroids C1, C2, C3 etc. Ck randomly, and look at all the data from that centroid of some radius epsilon 1 and do this. So, this works. The problem is it is restricted to this idea of centroid, which means basically circle types. Okay. So, you eventually end up with having data which are clustered like this. Okay. Of course, if they are too close, they all merge and become one big cluster. There are other techniques. Okay. So, the algorithm is a minimax algorithm. You minimize and maximize. You minimize the distance here, intra distance, maximize dj, which is inter distance. Okay. So, that is really the algorithm. But there are better algorithms. The better algorithms are hierarchical, okay. Then you also have other flavors of mixture models which overcomes this restriction of circular. So, you have another half a dozen better clustering algorithm, but intuitively this minimizing distance within the cluster, maximizing the distance between cluster groups, that is the best starting point. Okay. So, classification, and once you cluster you can pick a label for this and continue with the classification as you did for supervised classes. Of course, this is an iterative process, you keep doing, and this randomly selecting centroid, k number of centroid is again iterated. So, your first choice may not, but we know one thing, it is bound by 1 to n. So, you select some random k and then work out, go decrease, increase, then you will have some nearly optimal clustering. Yeah, this more or less finishes your classification and clustering. Regression models have also been done, which is attached with this, and Dr. Arul will do that for you. We will now move on to a more interesting, more common, more dominant methods of data analysis today, which is basically neural network and machine learning. Okay. We will briefly look at the elements of perceptron and how these things eventually end up with deep learning models.